What is time? It's a question that has puzzled philosophers, scientists, and pretty much every human who has ever stared up at the stars. For most of us, time is simply the clock on the wall or the calendar on our phone. It's the steady, relentless march from one moment to the next. It's the difference between yesterday, today, and tomorrow. We experience it as a continuous flow, an unceasing river that carries us from the cradle to the grave. For centuries, our best picture of time came from one of the greatest minds in history, Sir Isaac Newton. His view was simple, intuitive, and it worked for almost everything in our daily lives. Newton imagined time as a universal clock for the entire cosmos. In his view, a second passing on Earth was the exact same second passing on Mars, on Jupiter, and in the most distant, unknown galaxy. Time was absolute, a single, unbending ruler measuring the duration of all events everywhere, for everyone. It was completely separate from space. It was the background beat to which the entire universe danced, unchanging and unaffected by anything that happened within it. This idea feels right to us because it's how we perceive the world. But, as we got better at measuring the universe, we found cracks in this simple, elegant picture. The revolution came from another towering figure in science, Albert Einstein. Einstein looked at the universe and saw something far stranger and more wonderful. He proposed that time was not separate from space at all. Instead, they were woven together into a single dynamic fabric, space-time. And this fabric wasn't just a passive backdrop, it could be bent, stretched, and warped by the matter and energy moving through it. This radical new idea completely changed the game. It meant that time wasn't universal. Your clock could tick at a different rate from my clock, depending on how fast we were moving or how strong the gravity was around us. The door to time travel, once firmly shut, was suddenly cracked open. Not a rigid stage but a stretchy, flexible fabric. A planet. A star. Your own body creates a dip in this cosmic fabric. Objects follow the straightest path through curved spacetime. Time is part of the fabric. When spacetime warps, time warps too. One of the most mind-bending consequences of Einstein's special relativity is a phenomenon called time dilation. It sounds complex, but the core idea is simple. The faster you move through space, the slower you move through time. Remember, the speed of light is the ultimate cosmic speed limit. Nothing with mass can ever reach it. As an object accelerates and gets closer and closer to the speed of light, strange things begin to happen from the perspective of a stationary observer. The object's mass appears to increase, making it harder and harder to accelerate further. And most importantly for our story, its internal clock starts to tick more slowly. Let's imagine a classic thought experiment. You have two identical twins. One, let's call her Stella, stays on Earth. The other, an astronaut named Chris, boards a super advanced spaceship that can travel at, say, 99% the speed of light. Chris goes on a journey to a nearby star and back, a trip that takes him 2 years according to the clocks on his ship. But when he returns to Earth, he is in for a shock. Decades have passed. Stella is now an old woman, while Chris is only 2 years older than when he left. This isn't science fiction, this is real, measurable physics. We see tiny amounts with atomic clocks on planes, and dramatically with particles and accelerators that survive far longer because their internal clocks have slowed. In a sense, they are time travelers. Speed isn't the only thing that messes with the flow of time. According to Einstein's theory of general relativity, gravity does it too. The stronger the gravitational field, the more it curves space-time and the slower time flows within that curve. A clock at sea level will tick a tiny bit slower than a clock on top of a mountain. This effect is known as gravitational time dilation. It's a direct consequence of mass warping the fabric of the universe, and it has profound implications for how we navigate our cosmos. Let's take this to an extreme, near the edge of a black hole. A black hole's gravity creates a well in space-time so deep that not even light can escape. That boundary is called the event horizon. From a safe orbit, near a black hole, watching Earth through a telescope, you'd see life unfold in extreme fast-forward. Years, decades, even centuries and hours. Now flip it. Leo falls toward the hole. His ship's clocks tick normally to him, but to us, they slow. His motion drags, and his light reddens, until he fades at the edge. This isn't just theory. GPS satellites feel both effects. Speed slows their clocks. Weaker gravity speeds them up. Net. About 38 microseconds fast per day, and without correction, GPS would be useless. So, we've established that traveling to the future is physically possible. You just need to go very fast or hang out near a very massive object. But what about the holy grail of time travel? Going to the past. Our current understanding of physics based on Einstein's relativity doesn't strictly forbid it, but it says you'd need extraordinarily strange ingredients. The most famous involves a wormhole, an Einstein-Rosen bridge. Create a wormhole with two mouths, leave one near Earth, take the other on a near light-speed trip and bring it back. Its clock ages less. Enter the 2050 mouth and you emerge from the other in 2030, 20 years in the past. There's a huge catch. Theories say a wormhole would be incredibly unstable, collapsing before a single photon could pass. To keep it open, you'd need exotic matter with negative energy density, pushing space-time apart like anti-gravity. We've never observed it and we don't know if it can exist. So for now, wormhole time machines remain tantalizing but speculative. Let's assume for a moment that we solve the immense engineering challenges. We find some exotic matter. We build a stable wormhole. We create a working time machine that can take us into the past. The moment we succeed, we hit a wall of contradictions called paradoxes. The most famous is the grandfather paradox. A traveler goes back before their parents are born and kills their grandfather. Then the parent is never conceived. The traveler is never born. So who did the deed? It's an impossible logical loop. One idea. The self-consistency principle. Physics conspires to prevent contradictions. You can visit the past, but you can't change it to create a paradox. Any attempt that would alter history simply fails in mundane ways. The universe remains consistent. Physicists and philosophers propose alternatives too, each as mind-bending as time travel itself. Either way, cause and effect appear fiercely protected. Another proposed solution is the many worlds interpretation from quantum mechanics. Every time a quantum event has multiple outcomes, the universe splits into parallel branches, one for each possibility. In this view, killing your grandfather creates a new universe, where you're never born, but your original timeline remains unchanged. You haven't changed your own history. You've stepped into a different one. It avoids paradox at the cost of spawning a staggering number of unseen universes. Beyond paradoxes, time's one-way flow is tied to the second law of thermodynamics. Entropy tends to increase. Order decays into disorder. A pristine sandcastle crumbles, a hot coffee cools, an egg scrambles, but never spontaneously unscrambles. The universe began in a low entropy state and has grown more disordered ever since, giving time its arrow. Reversing that arrow would require fantastically improbable fluctuations, effectively zero on macroscopic scales. While journeys to the distant future and the ancient past remain theory, the principles of time travel are in your pocket. Every time you use GPS, you depend on relativity and time dilation. Satellites orbit high above Earth and experience time differently. Their clocks gain about 38 microseconds per day. That's huge for a system that times signals racing at light speed. Without constant relativistic corrections, errors would grow about 10 kilometers per day. So when your phone says, "Turn left in 200 feet," thank Albert Einstein. As of today, October 10th, 2025, we know time travel to the future is possible. Time dilation is real and measured. The journey of astronaut Chris returning younger than his twin is physically plausible, though far beyond our current tech. We are all time travelers, moving into the future at 1 second per second. To go faster, we must move much, much faster through space. Travel to the past remains a different story. It is not, to our current knowledge, possible. Wormholes and multiple universes are fascinating, but speculative, with no evidence they exist or can be created.